Our current test application works, but it has a couple of problems. First, it isn't part of a formalized test suite since it relies on our test application to exercise it. Second, it is only being tested by scenarios that we can think of which, while very repeatable, is not likely to find the situations in which the algorithm breaks down. To address these issues, I'm going to create a new source file in the package called math_test.go. After adding in the package declaration, I'm going to import three packages. The math package will be used by the test itself. The testing package is required to create a test for the test runner to execute, and the testing quick package houses the check function. Now I'll write a new test called test new integrator that will compare the results of the two integrators and make sure that they remain under the 1% error margin that we have been given. Inside of the test, I'm going to create an instance of each of the integrator objects and then start to create the test function as a function literal that will be passed into the check function to execute the tests. As I've said, the arguments for this function are pretty arbitrary as long as the value function can generate a variable of that type. However, the function must return a boolean that indicates if the scenario was successful or not. Let me make one more note about the arguments that I'm using. The integrator interface expects the last parameter to be a variadic float64, describing the coefficients of each of the polynomial's exponents. I'm using a fixed array here for two reasons. One, the check function doesn't seem to understand how to work with variadic parameters, so I need to pass a slice or array instead and spread that out later. The reason I'm using an array is more academic. It is going to be easier to understand the output of this function if we aren't dealing with massive polynomials that could come from a slice being requested. Inside of the test function, I'm going to get the result of calling the two integrators and storing their values in local variables. I'm then going to calculate the error value by taking the absolute value of subtracting the two results and dividing by the first. If that's less than 0.01, then everything is happy and I'll return true. However, if it's greater than or equal to 1%, then I'll return false, indicating a failure. Now it's time to run the actual test. I'll do that by calling the check function and passing in the test function and nil for the configuration, meaning that I'm fine with the defaults. If the error does not come back as nil, then the test has failed and I'll dump the error object to the log via the error method. Okay, let's run this thing and see what we have. I'll run the tests on the package and wait a bit for them to finish. Looks like we have a failure here. Since I dumped the resulting error object, let's check it out and see what we have. It turns out that the error object that is returned is of the type checkError, which, in addition to implementing the error interface, contains data on which run failed and what the inputs were. In this case, we see that this was test case number 1 here, and we get the values that were passed into the test function. The issue comes from the fact that these huge values of the float64 are actually too big for the integration to handle, since we are raising the values exponentially and, therefore, blowing way past the maximum value that a float64 can hold. This edge case, however, might never happen in production, but the point of the check function is to show that this is an allowable scenario, and when used, it will generate errors. At this point, we would probably have to go back to the customer and ask for further requirements about what is the maximum input values that they expect. For now, let's just imagine that we are allowed to constrain the exponents to never be greater than plus or minus 128, which means that we can change the test function to receive byte values instead of float64s. Now that doesn't change the production code, so I'm going to need to coerce these bytes back into floats. Pardon me while I use a magic fade out to jump to the end of that. Okay, that's all done, so let's rerun this thing. I'll open up the terminal and rerun the tests. We failed again. But we made it quite a bit further this time. It seems like test case 40 is where we ran into problems, and I think that this comment here might be the clue. If you look at the test logic, you'll see that I'm calculating the error factor by dividing the difference of the sums by the first result. What do you think will happen if the first result is either 0 or a very, very small number? Yep, a divide by 0 error will occur, and boom. This issue needs to be resolved by making our test logic a bit smarter. I'm going to start by checking to see if the results are both 0. If they are, then we have a match and the test case passes. If the first result is 0, but the second isn't, then I'll calculate the error by using the second result as the denominator. Finally, if the first result isn't 0, then we can use the original error calculation. Okay, let me spin this up one more time. There we go. After a bit of refinement, we now have a test that guarantees that, within certain limits, we can use Riemann sums as a replacement to polynomial integration in our application. Next up, we'll use the check equal function to determine if two independent functions give the same results.